Hi everyone, we're gonna go ahead and get started. So today we're going to understand the underlying logic of the recursion algorithm through a very interesting math puzzle towards Hanoi. There was once a very famous computer scientist said that to iterate is human, to recurse divine. So today we're going to take everyone go divine. Let's get started. Understand recursion, which is also the optimal solution to any towers of Hanoi. Recursion, in definition, is the process of defining a problem in terms of the simpler version of itself. Well, this sounds complicated and confusing, right? So let us first look at the game Hanoi. If we are not familiar with this game, let me first introduce you how we can play this game. So our goal is to move all of these disks from the first rod to the third rod in this exact order, from small to large. And there are three rules that we have to follow. The first one is we can only move one disk at a time. And the second one is we can only move the uppermost disk of each of the rod. And the third rule is that we can never put a larger disk on top of a smaller one. And let me just show you guys a demo. And yeah, that is how we play the game. Now, let's talk about how we can find the optimal solution to those towers of Hanoi through recursion. Well, the approach to any kind of the problems, puzzles, or games can be divided into three steps. First, trying to solve for the simplest case of this exact problem. And then second, trying to summarize the patterns from more complicated cases or different situations. Then finally, we generalize this pattern and apply it to any versions of this particular problem. Problem solved. So now, the first step, what is the simplest case for those towers of Hanoi? Well, it is just when there is only one disk, when n equals to 1, and n refers to the numbers of the disks. And what do we do when there is only one disk? Well, we just simply move. Since there is only one disk, and this move obeys all of the three rules that are stated above, we only moved one disk at a time, and the disk itself is the uppermost disk of this first rod. And right now it is on top of nothing, so obviously it is not on top of the smaller one. Problem solved. So what if there are two disks? Let's see. When n equals to 2, if we try to move these two disks to the third rod in this exact order, we have to move this larger one to the bottom, right? And in order to move the larger one to the bottom, we have to first move the smaller one to the spare rod. And then we move the larger one. After we move the larger one, we move back the smaller one on top of it. Again, problem solved. It's kind of easy, right? So now let's look at some of the more complicated cases. For example, when there are three disks, when n equals to 3. Now this problem became a little bit tricky, but fortunately, we can learn from the experience we gained from the last example. So in the last example, when there are two disks, before I can move this bottom disk to the target rod, I have to first move everything on top of it to the spare rod, right? Since we can only move the uppermost one. And then we can move the bottom disk to the target rod. And finally, we move back everything to its top, right? That is how we solve the last example. And now we can apply the same strategy to the case when there are three disks. So in this case, what we want here is we're trying to move everything on top of the bottom disk to the spare rod, so that we can move the bottom disk to the target rod. And finally, we move back everything to its top, right? And now you guys probably gonna ask me, why I can move two disks? Like, how can I move two disks? Well, this is where things become interesting. So in the last example, we already know how to move these two disks from the first rod to the third rod, right? And the endpoint, sorry, the end rod has no impact on how do we move these two disks, right? It's the same, either from the first rod to the third rod or from the first rod to the second rod. And in this case, it requires us to firstly move these two disks from the first rod to the second rod. And in this subtask, the third rod becomes the spare rod, since the second rod is the target rod. So we firstly move everything on top of the second disk to the spare rod, so that we can move the bottom disk of this subtask to the target rod. And finally, we move back everything to its top, so that we can move the real bottom disk of this to this real target. And now we have another subtask, which is to move these two disks from the second rod to the third rod. Well, in this case, the first rod becomes the spare rod. So we firstly move everything to the spare rod so that we can move the bottom disk. And finally, we can move everything back to its top. Problem solved. Well, the same strategy still holds true when there are 4 disks. And we firstly move everything on top of the bottom disk to the spare rod so that we can move the bottom disk. And finally, we move back everything to its top. And how do we move the 3 disks? Well, we already know from the case when there are 3 disks. And how do we move 2 disks? Well, we already know from the case when there are 2 disks. And how do we move 1 disk? Well, we already know it's just simply move. All right. We seems to find a pattern here. And let's summarize this pattern from a tree diagram. Now, let us create a function using pseudocode to better understand these situations. So I write a function called optimal solve. And what does this function do is it helps us to solve the Hanoi game in a optimal form, and which takes 3 parameters. The first one is n, which refers to the numbers of disks. And it also has to know where to start and where to end. So it takes 2 position parameters called start rod and the end rod. And now let's look at how we can write down our strategy in terms of these functions. So if we want to solve the case of 2, we want to firstly move everything on top of the bottom disk, which is 1 disk, from the start rod to the spare rod, so that we can move the bottom disk. And after that, we want to move back everything, which is 1 disk, from the spare rod to the end rod. And writing in the form of this function is optimal solve 1 spare end. And now let's look at the case of 3. And what we want here is similarly, we want to move everything on top of the bottom disk, which are 2 disks, from the start rod to the spare rod. And then we can move the bottom disk. And after that, we can move everything back from the spare rod to the end rod. Problem solved. And the interesting thing here is we can break down the case of 2 into 2 cases of 1. And also we can break down the case of 3 into 2, the case of 2. And each of these 2 cases of 2 can be further divided down into 2 cases of 1. And that is how we call it recursive function. Now, let's formalize these patterns before we can actually start to write some code in Python. The pattern. So if we want to optimally solve the case of n, we want to firstly move everything on top of the bottom disk, which is n-1 disks, from the start rod to the spare rod, so that we can move the bottom disk, which is the nth disk. And then finally, we want to move back everything, which is n-1 disks, from the spare rod to the end rod. Problem solved. Now, let's write a recursive function in Python to help us solve the Towers of Hanoi game. So I will first define a function called optimal solve, which takes 3 parameters. The first one is n, and n refers to the number of the disks. And it also takes two position parameters, the start rod and the end rod, which only take integers from 1 to 3, which represent the first rod, the second rod, and the third rod, respectively. And since I'm not going to do a fancy animation on that, we're just going to simply print out the instructions of the move. Now, let us start to write the function. If n equals to 1, we are just going to simply move the nth disk, which is also the first disk, which is also the bottom disk, from the start rod to the end rod. Problem solved, right? So let us look at some other cases. Remember our strategy here. So if n is any other positive integer that is greater than 1, we want to firstly move everything on top of the bottom disk, which is n-1 disks, from start rod to the spare rod, right? Remember that? So let us first write that down. We want to optimally move everything on top of the bottom disk, which is n-1 disks, from the start rod to the spare rod. But the problem here is the Python code doesn't know what is spare rod, so we have to define it for it. But how do we know the value of spare rod? Well, it's simple. We're just going to do some number manipulation here. So we know that the start rod and the end rod only take integers from 1 to 3, right? So we can use the sum of 1, 2, and 3 minus the value of the start rod and the end rod to get the value of spare rod. It sounds confusing, right? But we are going to first write that down and then take some example. So you can see here, if we want to move everything from the first rod to the third rod, the second rod is spare rod, right? And the second rod 2 is equal to 6 minus 3 minus 1. And the same thing still holds true for other situations. 1 is equal to 6 minus 3 minus 2, and 3 is equal to 6 minus 1 minus 2, etc. And let's move on. So after we moved everything on top of the bottom disk, now we want to move the bottom disk, which is also the nth disk. Now let's write that down. We want to just simply move the nth disk from the start rod to the end rod, right? And let's back to our strategy here. So after that, then we want to move everything back from the spare rod to the end rod, right? Let's continue. We want to optimally move everything back, which is n-1 disks from the spare rod to the end rod. Then problem solved. Now let us look at some examples to see if it works. So if we want to move 3 disks from the first rod to the third rod, let's run the code. Yeah, we got the instructions. So let's see if the instructions are correct. So it let us first move the first disk from the first rod to the third rod, then move the second disk, then the first disk again, the third, then first, second, first. It works. Now you can try some other examples by yourself.